Okay, so we're on line 18A3K. This is Lenz law, energy, volts, magnetic flux, EMF, proton, momentum, Wow Seti, part 115. That's for the Wow Seti signal. And this is Lenz law here. It's a common way of understanding how electromagnetic circuits obey Newton's third law and the conservation of energy. Lenz law is named after Heinrich Lenz. This is Heinrich Lenz there. And it says an induced electromotive force, EMF, always gives rise to a current whose magnetic field opposes the original change in magnetic flux. Lenz's law is shown with the minus sign in Faraday's law of induction, which indicates that the induced EMF and the change in flux have opposite signs. Opposing currents. If the magnetic field of current induces another current, the direction is opposite of it, and if these currents are in two circular conductors, respectively, then the currents must counter-rotate. The opposing currents will repel each other as a result. Detailed interaction of charges in these currents. In electromagnetism, when charges change positions along electric field lines, work is done on them, whether it involves storing potential energy, negative work, or increasing kinetic energy, positive work. Kinetic energy kept coming up in the data before. When net positive work is applied to a charge, Q1, it gains momentum. The net work on Q1 thereby generates a magnetic field whose strength in units of magnetic flux density, 1 Tesla equals 1 volt second per square meter, is proportional to the speed increase of Q1. We were talking about velocity and speed in the alien message, and also electronic volts came up before as well. Those, I believe, were in either line 17 or line 18 data. The energy density of magnetic fields tends to vary by the square of their magnetic field's intensity. However, in the case of magnetically non-linear materials such as ferromagnets and superconductors, this relationship breaks down. And we have field energy, and then conservation of momentum. Momentum must be conserved in the process of, so if Q1 is pushed in one direction, then Q2 ought to be pushed in the other direction by the same force at the same time. However, the situation becomes more complicated when the finite speed of the electromagnetic wave propagation is introduced. See retarded potential. This means that for a brief period of time, the total momentum of the two charges are not conserved, implying that the difference should be accounted for by the momentum in the fields as speculated by Richard P. Feynman. And there he is there. That's what he looks like. Famous 19th century electrodynamist James Clerk Maxwell. This is James Clerk Maxwell. Called this the electromagnetic momentum. Although this idea is not generally accepted as a part of standard curricula in physics classes as of 2010. Yet such a treatment of fields may be necessary in the case of applying Lenz's laws to opposite charges. It is normally assumed that the charges in question are like charges. If they are not, such a proton and electron, the interaction is different. An electron generating a magnetic field would generate an EMF that causes a proton to change its motion in the same direction as the electron. At first, this might seem to violate the law of conservation of momentum, but of course, such an interaction indeed conserves momentum once taking into account the momentum of electromagnetic fields. This is source. It looks like that. Source distribution. The retarded potential formula describes the scalar or vector potential for electromagnetic fields of a time-varying current or charge distribution. The retardation of the influence connecting cause and effect is thereby essential. Example, the signal takes a finite time corresponding to the velocity of light to propagate from the source point of R to the field point of R, when effect is produced or measured. So from R to R. Otherwise, the formulas below correspond to the same superposition principle in electrostats for Coulomb's law. Okay, so that's the end of 18A-K, and next one is 18A3M.